So thank you to the organizers for inviting, well, technically my postdoc to this conference, but she has been since moved on to industry, so I'll be giving this talk in her stead. And we will be talking about probing glassy colloidal systems with active particles, or, well, I prefer perhaps disordered colloidal systems with active particles, and maybe if there is sufficient time, we'll get back to that. What I will be talking about was computational work done by my postdoc Clara Abarrea Velasco and my PhD Maaike Bos. Experiments were carried out in the group of Clemens Mechinger at the University of Constance, originally by Celia Lozano and later by Narinder. So let me give a quick, or well, somewhat lengthy introduction into the topic, because maybe not every one of you has seen all of these aspects of the systems that I will be talking about yet. So the first types of experimental findings I would like to talk about is experiments originally carried out in the group of Clemens Bechinger by Juan Ruben Gomez Solano, who put in active particles, so the ones similar to the ones that we've seen before, but a slightly different propulsion mechanism, in a viscoelastic or a dilute polymer suspension. And this is a big colloid, so we're talking about a couple of microns in diameter, and so the rotational diffusion dynamics is rather slow. And because it's a half moon shape in a optical microscope, you can just track the half moon shape and you get a feeling for its orientation. And so one of the more interesting results that they found was that if you start adding a little bit more polymer, but we're really talking about a smidgen of polymer here, the more polymer you add, the more curved these trajectories become, or in other words, the greater the rotational diffusion coefficient becomes, and that what you see here. And the Weissenberg number here on the bottom is a standard measure of a rheological parameter for viscoelasticity. And what we see here is if I add a little bit of polymer to the system and I divide out the bare diffusion coefficient without any polymer, then what is the value that I get? And it should be mentioned here that the activity couples to the linear transport, not to the rotation of the particle. And what one sees is that one gets about like enhancements of even a factor of a couple of hundred, which is extreme. And the other aspect which is very interesting about this is this happens at extremely low Weissenberg number. And extremely low, you should think of this in terms of the theoretical prediction is if you make a series expansion of coupling between translation and rotation, well, in a Newtonian fluid, so no polymers added, just plain water, for instance, you don't get coupling between translation and rotation for a sphere. In a viscoelastic fluid, you do, but the series expansion comes in at Weissenberg order squared for translation and rotational coupling. And so to have such a significant effect at such small Weissenberg numbers is at least surprising. Now, all of this was understood heuristically in a very simple model where they take into account viscoelasticity. And how do they do that? They have a parallel coupled damping and elastic contribution to the behavior of the suspending fluid. And the only thing that this does, and provided there's enough time, I'll get back to that, is it says particle points into this direction, and there is a noise, thermal noise, which reorients it. But because the medium is now viscoelastic rather than Newtonian, there's a memory of what the particle was pointing in originally, and that memory contributes a torque, which would be absent in the case of a Newtonian fluid. And so that's what then generates this rapid reorientation. But this is a very heuristic model. So how would you go about testing the heuristic knowledge? Well, you say it's a viscoelastic memory effect, then you should try it for some other viscoelastic medium. and see if those kind of concepts still work. So let's move on to the next slide. Before we do that, I wanted to point out that this kind of effect has also been modeled with explicit polymers in the group of Gerhard Gompe. And interestingly, here they do see a little bit of an enhancement when they simulate it with these polymer chains, but it's rather limited. And if I were to believe this set of curves, all of the enhancement would have to happen at, well, exceedingly low polymer volume fractions, because yes, this point goes through 1, but it has jumped up to the almost the full value within, let's say, 1% or so. So that is a bit, one has to be a bit careful there. So even a simple, well, not a detailed simulation model doesn't really capture all of the effects. Now, going back to the question, okay, so this viscoelastic aspect, well, we've looked in the previous talk at a dense suspension of spherical particles. If you use instead 2 types of spheres, like 2 different diameters, ratio 1 to 1.4, then you can get a glass, and I don't really want to use the term glass here because that's a little bit controversial, but what happens is that before the glass, you get a viscoelastic response of your effective hard sphere colloidal medium, and beyond the glass, you essentially have a solid with also elastic properties. And if you put a probe in there, you also see this enhancement. It's a little less, but the probe is also, compared to the glass beads, is considerably bigger than the probe would be compared to a polymer. And the solid lines here are a theoretical prediction based on this heuristic modeling. So again, at the glass transition, it spikes, and that is also where one would expect the viscoelasticity to be greatest. And here what they have measured is they've measured this relaxation time in the fluid, and that has a different property both in the pre-glass fluid-like phase and in the more solid-like phase, and that corresponds to also the difference in decays on the either side of the glass transition. Okay. And then another thing which I wanted to point out of people having looked into this is this study in the group of Katz at MIT, where they took spheres, just uniform spheres, and a squirmer model, which is a simple form of self-propelled particle, where the entire flow field around it is modeled. And they observed that even in this system, you get a rather significant rotational diffusion enhancement. And here, what they write down here is the Peclet number, which is the amount of self-propulsion. And for experimental systems, you should think about a Peclet number of 100 is not unreasonable. So they are in the right ballpark, at least. But they, well, one, it's monodisphere spheres, so those definitely don't glass in 2D. And the other thing is getting to the properly high densities related to classy dynamics and using lattice Boltzmann is actually not that simple. So this is kind of the picture that we were faced with, and we were wondering several things when we saw all of this. Are there underlying generic features? Well, viscoelasticity certainly suggests that, but what is the minimal model to capture this physics? And then these 2 questions are kind of hinting at, is viscoelasticity necessary? And then there's a final question that I would like to ask, but we'll have to see if there's enough time. Do the timescales make sense? As in, do the timescales related to this dissipation and this elasticity actually make sense, or is there some fudging going on there? There's obviously some underlying generic features. I would say that viscoelasticity is not so much necessary. I would go for reorientation and disorder model. Viscoelasticity is a co-emergent effect in the experimental systems, and do the timescales make sense? Future work and possibly the final wrap-up bit of this presentation. So how do we model things? Well, we mimic the experimental conditions as much as possible. So we take the same aspect ratio, we take a WCA, so strictly repulsive interaction potential, Brownian dynamics of the colloidal passive spheres, confine it to a quasi 2D environment. Here you see some gray spheres indicating that, yeah, this is a regime of mostly cage rattling. And then the red one is an active particle, and that is burrowing its way through the sample. So very similar conceptually to what you saw in Sophie's talk. The only thing wherein we differ is that there's a softness to the WCA, and we vary that. And once you're in this soft interaction regime, you generate an angular velocity, which is based on a very simple rule that says you have a component which is perpendicular to the normal vector, and you project out that with the velocity, and that generates a rotation, which is essentially a rotational friction model, but it's also a very minimalistic view on this matter. Now, if you do that, then you can immediately get the asymmetry out of your system. So the rotational enhancement goes up more steeply, less steeply than it goes down, close to the peak in the enhancement. And you should think of the rotational diffusion enhancement in this specific system as being caused by every probe particle sees this cage structure, and whenever it contacts parts of the cage, it reorients, and then it finds a minimal, kind of the weakest spot in the cage. So this thing, every cage is a orientational potential landscape, and it can escape through cracks in every cage. And so it hops from one reorientational landscape to the other. This is a random process because it's disordered. And so the effect of all of these hops and all of these different landscapes is, in the end, something which has an effective Brownian signature. So then where does the peak come from? So we took a bunch of different softnesses, so very hard repulsion, so almost hard sphere-like, to something which can overlap quite significantly. And we see that with softer interactions, you get a greater enhancement, and that makes a lot of sense because you have essentially a larger zone of interaction over which you can generate these reorientations. And you decay less steeply above this transition. And so then we can also measure this rotational translational correlation effect, and we see that there's spikes here as well. So where does it come from? So one of the things which is very interesting is we can measure the number of the expectation value of the number of nearest neighbors. And if we do that, then we see that essentially, if we measure the inflection point in that nearest neighbor curve, and this is a bit rough, but that falls very well on top of the maximum rotational enhancement. So what we do see in our simulations is that the local environment in the passive system determines this maximum enhancement, and it's essentially somewhat of a second order phase transition in soft contacts. And so then returning to the polymeric system, where previous explicit studies of the polymers didn't show a great deal of enhancement, how should we then perhaps see this within our minimal model? So we looked up some of the numbers, which are unfortunately not published in the PRL. So the persistent length is 18 million. And so if you crunch all the numbers, you get a radius of gyration of each of these polymer blobs of 300 nanometers and a size ratio of 1:10 with the probe. Interestingly, if you crunch that and assume this blob to be this very soft deformable sphere, you get a volume fraction of 2.4. So you could imagine that you're kind of somewhere on such a or even a softer curve, somewhere the beginning end. And whilst we don't know the exact nature of the microscopic dynamics, you could certainly see that you would be able to create potentially create a large amount of enhancement in such a model. Interestingly, the size ratio is also very important. If you get a greater size ratio, you'll be able to generate more enhancement up to such a point that the local anisotropy becomes disappears again. So then within our model, let's click further. We do get a memory effect in the velocity autocorrelation function. So in a Newtonian fluid, the velocity autocorrelation function decays exponentially. Here we get an initial stretched exponential, which is already indicative of multiple timescales being relevant. Presumably the multiple timescales relating to the gap sizes in the cage, and then a power law decay. So there's definitely more going on there than just simple uncorrelated decay. And obviously within our system, we do see that the elastic modulus increases close to where we find maximum enhancement. There are a couple of questions still left here then as to, can we now couple these two scales? Looking at the clock, I will first do the conclusions, and if there's still some time left, I might show you a little bit more about these time scales. So we found that the rotational diffusion enhancement can be explained simply by disorder in the underlying environment, coupled to rotational and and a coupling of translation and rotation, with maximum enhancement at second order transition in contacts. The memory effect, which has been used to model this previously, we would consider to be emergent in our, and we can show that happens within our model. And viscoelasticity is also an emergent property of the disordered nature and density of the passive system rather than, well, that is just something which is rather standard. Then I'm going to have to ask the chair, do I get a few more minutes to talk about timescales?
I think you do have a few more minutes, yes.
Okay, so then I would like to talk a little bit more about the timescales. And so the first thing I wanted to give a flavor for is that this timescale story is actually rather complicated. So what you do is you take this these relaxation time curves that gives you this kind of this function, then you turn that into a correlation, correlation kernel that you convolve the instantaneous active velocity with. That becomes a drag force. Then the drag force crosses with the velocity function again, and this I haven't shown here also gets this kernel, and then that goes into this differential equation, which you then solve numerically to get the solid line. So I was actually very surprised that all of this worked very nicely in terms of the experimental system. But we have looked at spheres thus far, and the polymers you could maybe argue is like a blob. It might average out as to being some kind of symmetric object. If we want to really know about the timescales and which ones are relevant, we should do something else. And that's where we're working on presently is, well, you can also make a glass with colloidal rods. And here you get silica rods, which are kind of 10 nanometers long and 10 micrometers long and about a micron in width. And again, you get rotational diffusion enhancement. So this is a little bit more raw data, so it's not been nicely normalized with the bulk diffusion coefficient. But clearly systems of rods show rotational diffusion enhancement as well, by about a factor of 12 or so. And the cool thing about classes of rods is that there's three distinct timescales: one of translational glassy dynamics, one of rotational glassy dynamics, and one of diffusion in the perpendicular direction. And by what I mean by that is that if I were to have, say, my colloidal sphere, if it's really contact dynamics, you can imagine that any one of these smaller rafts of colloids is kind of periodically tapping the surface of my probe particle. And which one of these is the contributing one, we can now try to unravel in this system. And so that's what my PhD student is currently doing. So she started to simulate some rod systems, as well as the dynamics of a probe particle in such rod systems. And then the final thing I would like to give as a takeaway for you is that these probe particles are quite interested in probing the local dynamics and so on. And you have to realize that they are very different from other forms of active microreology in that the probe finds its own way through the system. So that's a very nice feature. So then finally some acknowledgements. Laura Villian, Frank Smallenberg, and Michiel Hermes from Utrecht University for useful discussions, as well as the Dutch Research Foundation, European Research Council, and the DFG for funding. And thank you for your attention.
Thank you very much for a wonderful talk. Let's clap virtually, and then I welcome your questions. Either unmute yourselves or let me know in the chat. And while people ask questions, let me ask a very broad question in terms of the motivation of the talk. Do you think of this sort of theory models as being a way to probe the passive material in which you have the active particles, or a way to construct kind of new active matter by putting more and more particles, in there? And
so the motivation for us really was to find kind of minimalistic ingredients, and then from that minimal model you can dial any number of knobs, and by dialing them you will find out some things about both the passive systems that you're probing as well as how activity couples to it, right? So the advantage of the more microscopically centered models is that yes, you will get something out of it, but you'll lose some of the genericness of it. I think that goes a little bit in the direction of your question, but
yeah, definitely. That's really interesting. Thanks a lot. We have a question from Emanuele. Okay.
Thank you very much, Joost, for the very nice talk. I have a question. I don't know if I'm saying something completely dumb or not, but could it be that the way you implemented this kind of rotation is a sort of a minimal way to include the hydrodynamic effect that the propulsion has on the propulsion?
Yes, that is one way of thinking about it, but there's a couple of different aspects to that. Let me see if I can quickly scroll back. So that would certainly be very much in line with the kind of conceptual things that Aragones did, for instance. There are experimental reasons why to think that it's maybe not necessarily strictly hydrodynamics, though near field flows are obviously could be quite vigorous. If you look at, say, what the Kaiki did in the group of Gomper, then what they did have these flows, but they found out that it was extremely necessary for them to have also attraction between the polymers and the surface of the sphere. So hints are going in a direction of a contact friction rather than just a hydrodynamic lubrication. The jury is still out on that, and there's also a couple of interesting hints in the experimental system which I kind of glossed over here. Let me just show you that. Whilst we have very similar shapes, there's actually a subtle difference is that in the experiments they always find a much lower glass transition. And in fact, the reason why I wanted to kind of avoid the discussion of glass is the experimental system seems to have much more of a strong glass type transition than any of our simulations of the passive systems have. Also being indicative of at least their kind of colloids experiencing perhaps some not rotational friction, but the other one. Yeah, the sliding friction. So there's some things which are also not in the passive system quite clear. Definitely in most of the simulation models, you would not get a proper glass transition, but the experiment definitely gives some hint of that.
Thank you.